I'm Jules, and this is joint work with Robbert, Krebbers and Balzer. Our paper originally came about because we tried to mechanize the deadlock freedom proof for session types, and it turned out that this was a bit more difficult than we originally
Okay, I think we
thought.
don't have sound right
So I will
now.
first explain what session types are and what the difficulties were. Session types are a type system for message passing concurrency. Here you see a session type for a channel C, and this session type describes the protocol with which we can use C. In this case, the first step is to send a natural number, the second step is to receive a Boolean, and the third step is to send a value which is itself a channel. Channels always come in dual pairs, which communicate with each other, and they have dual types. So when one side is sending, the other side has to be received. And this is joint work with Robbert, Krebbers and Balzer. Our paper originally came about because we tried to mechanize the deadlock freedom proof for session types, and it turned out that this was a bit more difficult than we originally thought. So I will first explain what session types are and what the difficulties were. Session types are a type system for message passing concurrency. Here you see a session type for a channel C, and this session type describes the protocol with which we can use C. In this case, the first step is to send a natural number, the second step is to receive a Boolean, and the third step is to send a value which is itself a channel. Channels always come in dual pairs, which communicate with each other, and they have dual types. So when one side is sending, the other side has to be receiving. And the way channels are originally created is if you spawn a thread, then one side gets one side of the channel and the other side gets the other side of the channel, so that the two threads can communicate with each other. We have to use channels linearly, which means we can't copy or delete a channel reference, and this is important for type safety. Suppose, for instance, that we could copy C, then we would be able to send this first natural number twice, whereas the other side is only expecting to receive one natural number, so that would violate type safety. So the fact that with linear types that this does satisfy type safety has been mechanized many times. But the type system for session types actually ensures much stronger properties, such as deadlock freedom and global progress. That is well known, but this has not yet been mechanized in a proof assistant. And this is what we originally set out to do. So why do session types give deadlock freedom? Well, in an untyped language, you could have simple deadlocks. So for example, if you have a channel and both sides try to receive at the same time, that would create a deadlock because they would wait for each other. So with the type system, this is ruled out because the two session types always have to be dual. But there can be more complicated forms of deadlock, such as deadlocks of threads waiting in a cycle. This is ruled out because the linear typing always maintains the acyclicity of the ownership structure. This is not obvious, and this was also one of the main difficulties in the proof, because channels can be used as first-class values, so they can be dynamically created, they can be sent as messages over channels, and because the channels are asynchronous, they can stay in the buffer for a while. They can be stored in data structures, they can be captured by closures, and so on. So this is really what makes the proof difficult, because maintaining this acyclicity requires reasoning about typing and about the graph structure of the configuration simultaneously. To make it possible to prove this in a proof assistant, we developed our connectivity graph proof method. This is a method for factoring out the graph reasoning from the reasoning about typing. We have mechanized this in the Coq proof assistant and applied it to prove deadlock freedom for a feature-rich session type language. The key idea of this method is that we usually want to work with an abstract representation of the runtime configuration. So here on the left, you see the runtime configuration row, and this configuration consists of threads and channels, and each thread has an expression, and each channel has a buffer. On the right, you see the abstract representation, which we call a connectivity graph, and the vertices in this graph correspond exactly to the threads and the channels in the configuration. We have an edge between a thread and a channel when the thread has a reference to the channel. We have an edge between a channel and a channel when the second channel is stored in the buffer of the first channel. So in the graph, we annotate the edges with the session types that the references currently have. In order to link this graph with the runtime configuration, we have this linking judgment. And this linking judgment expresses, first of all, that the graph is acyclic. And this acyclicity is in the following sense. So if you erase all the direction of the edges, then it's still acyclic. So it's really more, it's not a directed acyclic graph property, but more of a free tree property, so a tree without a root. So the second thing that this judgment expresses is that everything is well typed. So for a thread, that means that the channel references stored in its corresponding expression in the configuration have the types indicated by the edges. For a channel, we also have some kind of invariant between the values in the buffer, the session types on the incoming edges, and the session types on the outgoing edges. That's a little bit more complicated. You can see our paper for details. Let's look at the theorem that we want to prove in more detail. We start out with some initial configuration row 1, which consists of a single thread with a well-typed expression, and then this configuration steps using the operational semantics. And then at some point, we want to show that either this configuration is finished or it can take another step. To do this, we set up the proof similar to proofs based on progress and preservation. So we first create a connectivity graph which corresponds to this initial configuration and show that it is linked with it. And then we use a preservation proof to show that if the operational semantics takes a step, then we have a connectivity graph corresponding to the new configuration, and that is also linked with it. We continue like this until we are at the end, and then we use a progress proof in order to show that from the existence of this final connectivity graph and the fact that it's linked with row 4, we have a new configuration row 5. The connectivity graph framework that we have developed helps with proofs like this. It consists of these components. First, we have a connectivity graph data structure for acyclic labeled graphs, which is parametric over the vertices and the labels. Secondly, we have a generic construction for this linking judgment, which is parameterized by local separation logic predicates for each vertex in the graph. And those separation logic predicates then say things like the expression of a thread is well typed with respect to the outgoing edges, and for a channel they say that the values in the buffers are well typed with respect to the outgoing edges, where the types of the values in the buffers are determined by the incoming edges. So these predicates can talk about the incoming and outgoing edges of a vertex, but not about anything else in the graph, which makes them local. Thirdly, we have tools for proving the preservation step, and we do that using graph transformations expressed in separation logic. And those graph transformations then automatically also maintain this linking judgment. For the progress step, we have an induction principle on this C-graph data type, which lets us find a thread that can do the final step from row 4 to row 5. All these constructions are completely generic over the vertices and the labels, so they know nothing about the language that we are proving deadlock freedom for. You may ask yourself, why are we using separation logic? Isn't separation logic for proving pre and post conditions of programs? And that's indeed the way separation logic is usually used, but we were inspired by Arjen Rauwvoet's definitional interpreters to use separation logic in a meta theory for doing meta-theoretical proofs. So the advantage of separation logic is that this allows us to express the runtime type system in a much more succinct way. So on the left, you see a usual runtime type system rule. So in this runtime type system, we have an additional context sigma, which stores the typing associations for all the channel references. This context doesn't appear in the original static type system because in a static program, there are no channel references, but as the program steps, the expressions can contain channel references and we need an additional context to deal with them. So this context in our case has to be linear because channels are linear values, and this leads to these kind of disjointness conditions on each typing rule. The separation logic rule on the right is completely equivalent to the one on the left, but all these disjointness annotations are hidden in the separating conjunction, the star that you see in the middle. There is one rule that doesn't follow the pattern that you see above, and that is the rule for typing a channel reference. So for that rule, we need to look up its type in the sigma environment. And because the environment is linear, we also have to insist that this environment is in fact a singleton. In separation logic, we do that using the own connective, as you see on the right. At the end of the day, the sigma context gets instantiated by the outgoing edges of the vertex. So that way, we can talk about ownership over edges inside the separation logic. And this typing judgment is then used for the invariant of a thread, but for the invariant of a channel, we also have some kind of buffer typing judgment also expressed in separation logic. The advantage of this is not only in the typing rules, but also in the lemmas that we state. Here you see the classical lemma. This is usually called the replacement lemma, and that allows us to talk about evaluation context, and we can split a typing judgment of an expression in an evaluation context into a typing judgment about the expression and another judgment about the context. You see that this statement of this lemma is cluttered with things about these sigmas. So in separation logic, this becomes much simpler. The statement of the lemma becomes shorter, and a second advantage is that we can now prove these lemmas inside the separation logic proof mode of Iris. And this then automatically takes care of all these disjointness conditions that otherwise would pop up. Separation logic also turns out to be very useful for the preservation proof, but let us first think about what the preservation proof entails. So we have some kind of runtime configuration that steps, and we want to also come up with a new connectivity graph for the new configuration. So to do that, we modify the old connectivity graph by local graph transformations. Here you see the rules for the channel operations. On the top, let's focus on the rule for send. We have a thread T1 that has a reference to C, and the session type of its edge indicates that we are currently allowed to send a value of type tau. So T1 has a value of type tau, which may itself contain channel references. So here you see that in the green box V, which contains other channels. After sending this value to the channel, it ends up in the buffer. So the source of all the edges to the channels in V have to be redirected to be connected to C. Secondly, the edge from T1 to C has to be updated to reflect the new state of the protocol. For receive, the situation is similar but opposite, because the value now gets transferred out of the buffer to the thread. For fork, we allocate two new vertices in the graph, namely one vertex for the channel and one vertex for the new thread. So this channel connects the old thread with the new thread, and the session types on those edges are dual. The new thread also gets a value which it can use to initialize its execution state. Lastly, we have close, which just deletes an edge between T1 and C and also deletes the vertex if that was the last edge. So all these transformations, they preserve this undirected acyclicity of the graph, and they also preserve these local predicates that hold for each of the vertices. So it also preserves this linking judgment. Showing this, however, is complicated if you want to do it directly, because you have to reason simultaneously about typing and about this graph. So what we do instead is we abstract all these graph transformation rules in separation logic. Here you see an example. I don't expect you to read this, but this is a rule that we use for send and receive. So this rule allows us to exchange separation logic resources between two vertices connected by an edge, and it allows us to update the label on the edge. All of this is explained in our paper. The final step of the proof, progress, means to show that our configuration can take a step. In order to show this, we of course need to know which thread can step. So not all threads can always take a step because they may be blocked on a channel, but we want to find some thread that can make a step. So intuitively what happens is that we annotate the connectivity graph with waiting dependencies, which indicate who is waiting for whom. So in this case, T1 is waiting for C1. That means that T1 is currently blocked on C1. So all these red triangles are derived from the runtime configuration. What we then do is we start anywhere in this graph and we follow the path in the direction of the waiting dependency. Because the graph is acyclic, we can't run into a cycle, so we will eventually stop somewhere. And that place will be a vertex with no outgoing waiting edges. Though it may have outgoing edges, reference edges, they cannot be in the same direction as the waiting edges. We then prove that the vertex that we end up at is always a thread, so it cannot be a channel. And we prove that this vertex has to be able to take a step. This would also seem to involve graph reasoning and reasoning about typing simultaneously, but we factor that out using a weighting induction principle. So this weighting induction principle encapsulates this process of stepping through the graph. That works as follows. So we have this relation R, which indicates this weighting direction. That gives a relation between each pair of vertices that indicates in which direction is the weighting dependency. And then the induction principle says to prove P of some vertex V, we can already assume that P holds for all vertices W, such that there is an edge from V to W and the relation holds, or there is an edge in the opposite direction and the relation does not hold. This induction principle then encapsulates all the graph reasoning and in the proof gives you exactly the hypothesis, the induction hypothesis that you need in order to complete the progress proof. We use this framework to prove deadlock freedom for an extension of Wadler's GV. So GV is a functional language with session type channels, and we extend it in several ways. First of all, we have unrestricted as well as linear types. So unrestricted types are the usual types that you're used to in functional languages, which you can copy and discard freely. So those are numbers, sums and products of unrestricted types, and unrestricted function types. So unrestricted function types are closures that cannot capture linear resources in their environment. Secondly, we have linear types, of course, for channels, sums and products of linear types, and we have linear function types. So linear function types can capture linear resources in their closures, but you have to use them exactly once, so you cannot call them multiple times or 0 times. Secondly, we add general recursive types, and this is really the most general recursive types that you can imagine. So we have recursion in session types, including recursion through the message, as you see here. So we have mu of x, and then x occurs recursively inside the message. And we also have recursion in the functional fragment. And using that, we can encode algebraic data types using recursion, sums, and products. We mechanize all this using Gay's method of using co-induction in the meta theory. And this allows us to keep these recursive types recursive. We initially only had global progress in our paper, because this is the standard notion that people prove. But our POPL reviewers responded, can your method prove something stronger? Because global progress is actually quite weak. As long as there's still one thread that can step, then global progress doesn't say anything about the rest of the configuration. So it could be that one thread is in an infinite loop and the rest of the configuration is in a deadlock. So we set out to prove a stronger property, and we formulated that as follows. So we call a partial deadlock a set S of threads and channels, such that all threads in S are blocked on a channel in S, and no references to channels in S come from outside of S. This is a little bit different than the usual partial deadlock freedom property that you're used to, but we'll come back to that soon. Secondly, we also formulated a notion of strong reachability inspired by garbage collectors. So we say that a channel is reachable if it is referenced by a reachable thread or channel, and this is inductively defined. And a thread is reachable if it can step or if it is blocked on a reachable channel. So this is really a bit different than the notion of reachability in GCs, because in GCs, all the threads are always reachable, and all the data from their stack is always reachable, regardless of whether they are in a deadlock or not. But in this case, we only say that a thread is reachable if it can step or if it is blocked on a reachable channel. And the idea there is that if the channel is already reachable, that means that someone else has a reference to it, so it may be unblocked in the future. So if we are blocked on it, we should also be considered reachable. Perhaps surprisingly, these two notions turn out to be equivalent, so they both simultaneously express some kind of memory leak freedom and deadlock freedom, which is intimately connected. The second lemma that we prove is that if any thread or channel is reachable, then we have global progress. And this can be easily proved by induction on this reachability, because at the end of the day, to be reachable, it must eventually be connected to a thread that can step. So that thread can then be made to step the configuration. The final theorem that we prove is that for well-typed initial programs, no partial deadlock occurs, and thus also all objects always remain reachable. We have mechanized all of our results in Coq. Our mechanization consists of 3 parts. Firstly, the generic connectivity graph library, about 5,000 lines of code. The language definition, 450 lines of code. and a language-specific deadlock and leak freedom proof, 1,700 lines of code approximately. So initially, we did try to prove this deadlock freedom directly, but the proofs got very complicated. The graph reasoning became intertwined with the language specifics. Our typing rules have these disjointness conditions on them, and sometimes they can only be proved via the acyclicity of the graph. So sometimes if the graph was not acyclic, then these disjointness conditions are actually false. So it really becomes intertwined with each other. And by encapsulating the graph reasoning in this connectivity graph library, everything became much more manageable because all these disjointness conditions are always automatically taken care of. Thank you for listening to our talk, and now we're ready for questions.
Okay, we have time for a couple of questions. Any questions from the audience? Yes. Okay.
Hey, very cool. I had a small question about your local graph transformations, which is why did you include an explicit close operation if the channels are linear? Why not just delete the edge when you use the channel to send or receive?
If you do a send and receive, then if the protocol has not been finished yet, then you need to keep the edge because you can continue to use it. And we have an explicit close because operationally, you don't know what the type on the edge is, so you don't actually know when you're finished. Only the type system knows that, but the operational semantics does not know that. So that's why we need an explicit close.
Okay, thank you.
Okay, any questions online? No? One more question from May.
Really fun talk. So I love this idea of using separation logic to obviate some of the need to do the dynamic modeling. How does this extend to the more complicated notions of session typing that have come out in the 10 years since the Wadler paper you chose to model?
So which notions are you talking about?
Recursive channels are already in your model, right?
Right.
Okay, I guess I'll take it offline because I do not want to enumerate this right now.
Yeah, sounds good.